Hey all, so the Physics C questions have been posted for 2021, and I thought I would take a look. Now there's two sets. We're going to be looking at set number 1 right now. I'm going to have a link to the actual solutions that I put together on my website as a blog post, but I thought I would start with the problem set 1. I'm going to try to get through all of them, as many as I can. Tonight, but both the Physics C, both sets of the mechanics, and then the E&M. But let's start with the mechanics, problem set 1 here. So a 0.5 kilogram fan cart is placed on a level horizontal track of negligible friction shown. The fan is turned on. The fan cart is released from rest and moves to the right. The cart travels along the horizontal track and then down the incline. Motion detector 1 measures the acceleration of the cart to 3 seconds. Then at 3 seconds, it starts going down. The fan exerts the same magnitude of force on the cart during the entire motion. The graph below shown A as a function of t. For each motion detector, the positive direction is always away from the detector. That's why it's like positive, it's moving away from 1, and then down here it's moving. Now let's look at these numbers. This is +2, so there's like 5 hash marks, so that means each of these is 0.4. So this looks like 0.8 meters per second, and this looks like minus 2.4 meters per second. In terms of the numbers and the constant acceleration, I'm sure we'll probably need that information later. On the dots below that represent the cart at 2 different locations, draw and label the forces, not components, that act on the cart at each location. Each force must be represented by distinct arrows starting on and pointing away from the dot. Okay, so up on the horizontal, we got gravity, normal force, down and up, and then we have a force to the right due to the fan. So I'm going to say upward force. All right, let's use a different color. Oops. Let's use blue. So we got an upward force, normal force, we got gravitational force, mg, and then we have the force from the fan. Okay, on the incline, we still have mg going down, but now the normal force is directed this way. And now the fan is directed down this way, because the fan is pointing, it's opposite of the direction of, because it's pointing behind it. So as it slides down, the fan is pushing air backwards. So it's causing air to cause a push on the cart this way. It's technically force of the air because the fan pushes air and the air pushes on the fan. But it's fine. I'll just call it force of the fan. Calculate the magnitude of the net force exerted on the fan cart when it's on the horizontal track. So we look at the the acceleration is horizontal in this case. So basically, that means mg and the normal force cancel each other out. So the net force is just the force of the fan, which is equal, so we always use net force equals ma, right? So here the fan force is equal to m times a. So during the horizontal track, it's what was the mass? The mass is 0.5 kilograms, and then the acceleration is 0.8. That's what we said. So it's 0.5 kilograms times 0.8 meters per second squared, and that's 0.4 newtons. Calculate the angle theta of the incline. So now we're going to look at the free body diagram of this guy, and we're going to say that the fan force is the same. Like this is still 0.4 newtons, because the fan has had a constant force the entire motion. What we have to do is we have to decompose, and we know the acceleration is down the ramp, so typically we sort of decompose the mg force into its in the direction in the y and then direction of the an x, and then this force here we carry in the x direction is mg cosine theta, and so therefore the net force in the x direction on this one is mg cosine theta plus the force of the fan, and that has to equal ma. Now, the acceleration during this time is a little bit different, right? This is A2, whereas this was A1, because A1 referring to the acceleration of the motion detector 1 and then motion detector 2. Now it's moving at 2.4 meters per second squared. So here we would say, this is not mg cosine theta. I'm sorry. My mistake. I was rushing there. That's mg sine theta. This is mg sine theta. Just look at the trigonometry. It's going to say cosine didn't sound right. This is sine theta as this component. So then we say we can solve for sine theta, right? So sine theta is going to equal ma2 minus the force from the fan divided by mg. And we know all these numbers. So this is 0.5. So then theta, what is theta? Is the sine inverse of this. of all of this. M is 0.5, acceleration was 2.4. 0.4 is the force from the fan, and then this is 0.5 times 9.8. So then we just use a calculator for this. Sine inverse of 0.5 times 2.4 minus 0.4 divided by 0.5 times 9.8. I get 9.4 degrees. Okay. Suppose careful measurement determines that the angle of the incline to be 3 degrees larger than that calculated in part C, considering the following explanation. The scale used to measure the mass of the fan cart was not calibrated properly before measurement, and this could account for the observed difference in the angle. Does this explanation sufficiently account for the observed discrepancy? Well, let's look at the entire calculation we did here. We had mg sine theta plus the force of the fan is equal to ma2. And then the force of the fan, what we found, it was just m times a1. So this is mg sine theta plus ma1 is equal to ma2. And notice that we didn't need to know the mass. If you divided both sides by m, these would all cancel. And so you just get g sine theta plus a1 is equal to a2. So this does not depend. So the answer is no. The angle does not depend on the measurement of m. Okay. Part C. The experiment is repeated for several trials, each with different angle for the incline. The acceleration of the cart down the incline measured for each angle. The graph below is to show the plot of the acceleration of A as a function of the sine of the angle. So they plot sine versus A. This is going to be nice because we derived this nice expression here that A2 was equal to g sine theta plus A1. Now, in this case, we're plotting the acceleration of A as it's going down the incline. So really, you could just say, like, this is my A. So, like, in terms of variables, this is my X, this is my Y, and so this G is my slope, and A1 would technically be the Y-intercept. You just sort of match that, like, in terms of Y equals mx plus b, right? Okay, so what? Draw a best fit line for the data. I'm not very good at these in the computer. I'm going to try to pick something, but let's say it looks something like that. That looks pretty good. I don't know. No one's going to argue with me that that isn't the perfect straight line through this data. And then I just want to pick 2 points that are kind of far apart from each other. Let's pick this point. Looks like it's right on a dot. I just want something where it crosses hash marks. So I want to say like that and that, for example. And then we would say calculate the experimental value for the acceleration due to gravity. So we need to find the slope because the slope should be g. So this is the point. If I were to plot the point here, this is 0.4 comma, what is that? 4. Each of these is 0.2, right? Yeah. 2, 4, 6. So this is 4.6. And this point down here looks like not 0.1. Each of these is 0.02. So that's 0.08. And the y value is 1, 2, 3. So that's 1.6. Right? And so we'd say this G is approximately equal to, oops, I keep changing the colors, 4.6 minus 1.6 over 0.4 minus 0.08. That would be the slope. Oops, forgot a parentheses. 9.09. That seems pretty good. Close enough to 9.8. My line wasn't perfect. You would really use an analytical tool to give you the best line, but this is what the best we can do on paper. If the cart were replaced with a second cart of mass 1 kilogram that has a fan that exerts the same magnitude of force as the original fan, how would you explain the given graph? Well, it's heavier, so you would expect the acceleration on the horizontal part to be less. So if we look at our equation that we had, A1 is the only one that's really going to be affected in terms of this graph because A1 is the acceleration on the horizontal part. And this would be less because you'd have the same force of the fan but a larger mass. So this one would decrease This is the y-intercept. Everything else would stay the same because g would be the same, and then these are your variables that you're plotting. So only the line would shift down. Shift down. Okay? This would be a vertical shift down. All right, second question. Block of mass m starts at rest at point A with negligible friction through the loop onto the horizontal surface where the block makes contact with a spring of constant k equals mg over 2r. All motion on the spring is horizontal direction. Point C is the highest point in the loop. Point B is the rightmost point in the loop. Express all algebraic answers in terms of this. On the dot below, which represents the block, draw an arrow that represents the direction of the acceleration of the block at point B on the figure. The arrow must start on a point away from the dot. So at point B, let's think about all the forces we're going to have. We're going to have gravity. And the normal force is always perpendicular to the surface, right? Normal force perpendicular to surface. So we have two forces like that. Anything else? There's no friction, and nothing else is touching the block. So those are all my forces. So that means that the net force is down and to the left if you add those two vectors. So, I mean, I made them the same magnitude, but you don't have no idea if they're the same magnitude. But something like this would be appropriate for A, because it has a component vertical down and a component to the left. Justify your answer. There has a component, has a force component down due to gravity, and left normal force. So net force is down left. And net force equals ma. The direction of the net force is the direction of the acceleration, right? Derive an expression for the speed v of the block at point B. Here we're going to use conservation of energy. So I'm going to say, what's the energy at this point and the energy at this point? So I'm going to say the initial energy starts with is only mgh. Okay. H is a given information, and the final energy at the energy, we won't call it EF, we'll call it E at B, the energy at point B. What does it have here? It has some potential energy, but it has some kinetic energy too. Now, in this case, it's 1/2 mv squared, which is the kinetic energy. But the h, what's the height above the ground, is the r of the circle, the radius of the circle. So this would be mgr. And then because there's no energy loss, because there's no friction or any other outside force that would do work, we would just say these two are equal to each other. So we're going to say mgh is equal to 1/2 mv squared plus mgr. I can divide out the m's, and I just need to solve for v. So gh minus gr is equal to 1/2 v squared. I can factor out of g, then multiply by 2, and then take the square root, and that equals v. Okay, derive an expression for the magnitude of the net force on the block at point B. So at point B, we've got the normal force, and we have mg. So we know what mg is. That's already given information, because we know m and g is a physical constant that we already know. The normal force is perpendicular to this surface, and it's the centripetal force. So if I look at the net force horizontally, the normal force is equal to mass times the centripetal acceleration, which is mv squared over r. Okay? So, but I know what v squared is. V squared is this thing without the square root. It's m times 2g h minus r divided by r. That's the normal force. And then the gravitational force is mg. And if you want the magnitude of the net force, these are at right angles to each other. So we do Pythagorean theorem to find the magnitude of the net force is the square root of the gravitational force squared plus the normal force squared. So therefore, the magnitude of the net force is equal to square root of mg quantity squared plus all of this squared. This would be 2mg h minus r over r quantity squared. Now, I don't know if they want you to simplify this. You could factor out an mg squared and maybe combine that into a fraction or something. I honestly wouldn't. I would just leave my answer like that. But there's maybe some simplifications you could do. It's going to be mg times some value if you wanted to factor all that out. but I'm just going to leave it like that. Okay, in terms of R, derive an expression for the minimum height, h-min, necessary for the block to maintain contact with the track through point C. So now we have to look at the scenario and we have to say, like, okay, as we're moving through point C, we have to if we maintain exact contact or just barely lose contact, that's when the normal force is 0. So we only have one force here, Fg, which would then equal, but it's moving in a circle, so it's subject. That gravity is equal to ma, that's the net force, equals ma, and it's centripetal acceleration. So we would say at point C, it would have to be going at, we'd have to say Fg is equal to mg, and that'd have to equal m times the centripetal acceleration, which is mv squared over r. Okay? So this is so if you can cancel the m's and you can find that you would need, in order to maintain, to go around there, you would need v squared to equal gr. Okay, multiplied by the r. That's what you need to make it go around without losing. If it goes any faster, then the normal force will have a little bit of force downward, and so then you're firmly in contact. So this is the smallest v needed. Then we do conservation of energy between A and C to see what the minimum height necessary to get that speed around. So we would say in this case, E0, which is mgh, has to equal the energy at A, which is 1/2 mv squared, the kinetic energy, plus the gravitational potential, which is mg2r. Why 2r? Because at point C, what is his height above the ground is the diameter of the circle, which is 2r. Okay, but I know v squared is gr, so I can plug that into here. So this is 1/2 mgr plus 2 mgr, and that's 2 plus 1/2, which is 5/2 mgr, is equal to mg h-min. The m's cancel, and the g's cancel, so h-min is 5/2 r. Okay? It is determined that h equals 0.3 and r equals 0.1 if the block is released from a height greater than that found in part C. What would be the maximum compression? So basically, assuming you made it around the loop in this scenario, you have no loss of energy here. All of this potential energy is just going to get converted into compressing this spring. Because the spring, I assume it has no mass. No mass in the spring. So we're just going to say that there's no loss of energy during the collision, and then it just fully compresses. So it's actually, you just say mgh is equal to 1/2 kx squared, and you can solve for x. X is equal to square root of 2 mgh over k. And now we plug in some actually, they gave us what k was. K is mg over 2r. See that? So this is square root 2 mgh over mg over 2r. The mg's cancel, and this becomes the square root, flipping the 1 over 2r, it becomes 2r, so it becomes 4rh. And so this would be the square root of 4 times 0.1 times 0.3. And I get 0.346 meters. Yeah, these are measured in meters. Okay. A graph has a maximum compression of the spring as a function of height as shown below. The height of the h-min is calculated in part C. Explain why section 1 appears a horizontal segment in the horizontal axis. Basically, when we're below h-min, we didn't make it around the loop. So it couldn't compress. It just fell off the track. So it never made it around the loop. Either it didn't make it around the loop and it slid back down, or yeah, I think what was part C? Part C was maintain contact. It fell off, so it probably fell off, or slid back down, slid backwards. Those are the kind of it depends on how low it was, but it never hit the spring. That's the key part. So it never hits the spring. So the compression of the spring is 0 because it never hits it. Then explain the reason for the shape of this graph. This is a square root graph dependency, because if you look at our equation here, X has a square root dependency on H. With H. And at H min, X is non-zero. That's why it jumps up like this. Because H min is non-zero. You can't plug in H equals 0. Because when H is 0, like it doesn't even compress it at all. It has to be a certain height. And once it's there, is a certain amount of compression automatically. Okay. Number 3. Triangular rod of length L and mass M has a non-uniform linear mass density given by lambda equals gamma x squared, where gamma equals 3m over L cubed and x is the distance from point P at the left end of the rod. Using integral calculus, show that the rotational inertia I of the rod about the axis perpendicular to the page and through point P is 3/2 ml squared, 3/5 ml squared. So what is I? We always do the integral of x squared dm. Okay, what's the differential mass here? dm is just the linear density times x, or times dx, this width of dx. So this integral becomes the integral of x squared times lambda dx. And we're going to integrate from 0 to L here, because we're going to go the entire length from here to here. And lambda is gamma x squared, so that's the integral of 0 to L, x squared times gamma x squared dx. I can pull out the gamma, that's a constant, and this is x to the 4th dx. And that integral is 1/5 x to the 5th from x equals 0 to L. Gamma is 3m over L cubed. Then times 1/5. When I plug in L, I get L to the 5th. When I plug in 0, I just get 0, so I don't need to subtract 0. Then what's our canceling? L to the 5th, oops. L cubed and L to the 5th becomes L squared. And then this is 3/5 ml squared. Okay. So that's the whole setup there. Hopefully, I just realized my camera might be blocking some stuff, but I'll try to not have that. Determine the horizontal location of the center mass of the rod relative to point P. Horizontal location center of mass is always the total integral of x dm. So center of mass is given by this equation, x dm over the integral of dm. But you actually know the integral of dm. It's the total mass. So this is the integral of x gamma x squared dx over m. So this is, again, factoring out the gamma, integral x cubed dx over m. That's gamma over m. 1/4 x to the 4th from 0 to L. We're integrating from 0 to L again over the whole length. And that is gamma, what did I say gamma was? Is 3m over L cubed. So this is 3m over L cubed over m times 1/4 L to the 4th. Let's see, these m's will cancel, and this will cancel and leave 1, so I get 3/4 L. Okay. For an axis perpendicular to the page, is the value of the rotational inertia of the rod around point P greater than or less than or equal to the value of rotational inertia around the center of mass? It is greater than, because if you're going to compare to the center of mass, which is around here, basically on average, like all the mass is tends to be over here, and it's further away from P than it is from the center of mass. So we would say that the mass is on average further from P than the center of mass. And that results in a larger I. Because if, in general, if the mass is further away from the point of rotation, then that's a larger I. Okay. Rod is released from rest in the position shown, and the rod begins to rotate around the horizontal axis perpendicular to the page and through point P. So we have a rod here. Oops. Does that look okay? Oh, yeah. Perfect. And it's going to swing down like this. On the axis below, sketch the graphs of the magnitude of the net torque on the rod and angular speed omega of the rod as a function of time, from the time the rod is released until the time its center of mass reaches its lowest point. Okay, this one was a little bit tricky when I first read this one. And I actually did pre-read the questions and pre-do some of them because I wanted to make sure that you guys had. But basically, think about you're an arbitrary point angle here, and we want to calculate the torque. Well, the only force acting on this guy is the force at the center of mass, right? And this thing is L. And so if you want to calculate the torque relative to this point, we're going to take the L, or this is 3/4 L technically, to the center of mass. We're going to say that 3/4, like the torque, is equal to 3/4 L cosine theta, because I want the portion of the length vector that's perpendicular to mg. So this is 3/4 L cosine theta. And then that times the force perpendicular to that, right? So mg is perpendicular to that, so then I get times mg. So that means the torque is equal to 3/4 mg L cosine theta. Okay? So intuitively, what you should think about is the torque is maximum up here, and then the torque is 0 down here. The torque definitely is going to drop to 0 at some point, and it's going to start at the largest point up here. But the tough part is to think about what is the shape of this what is the shape of this thing? So it should be decreasing, right? But you want to know, like, is it decreasing in a straight line or not? And this is actually very difficult because the angle is changing, right? So like as the angle changes over time, then the torque decreases. So one thing you could look at is you could look at the derivative of the torque, dt. And this is 3/4 mgl, and the derivative of cosine is negative sine theta. And no matter, like, these constants are always positive. This is definitely less than 0 for the angles we're talking about, because we're talking about from 0 to pi over 2. And from 0 to pi over 2, sine is always positive. So when there's a negative sign here, this is always less than 0. This implies that tau is decreasing. Okay, but we already kind of knew that physically. But let's look at the concavity by looking at the second derivative. This would be 3/4 mgl times negative cosine theta, because the derivative sine is positive cosine, so that negative sign still stays there. And this is less than 0. And what this tells you is that torque is concave down. Why? Because cosine is always a positive quantity from 0 to pi over 2, because we're basically in the first quadrant in our unit circle. So cosine and sine are positive, which means that this whole quantity is negative, so torque is concave down. So I would say it looks probably like this. It's concave down and decreasing. That's the shape of something concave down and decreasing. Now, how is omega related? Well, torque is equal to I alpha, and you know that alpha is the derivative of omega, right? So that means the slopes of omega should be proportional to the acceleration, right? It should be related to the acceleration, which is proportional to torque. So that means basically I need the slopes. So here I have a very large I should have a very large positive slope. And then by the time here, I should have about a 0 slope, because here the angular acceleration, which is the slope, should be 0. Here the angular acceleration should be max, which is a slope. So then it should look kind of like that. And this kind of comes. So that's the general shape we should look at. Okay. As the rod rotates from horizontal position down to the vertical, is the magnitude of the angular acceleration of the rod increasing, decreasing, or not changing? Well, we just calculated this. The magnitude of the angular acceleration, that means I need to know, is this is the magnitude of the angular acceleration. So torque is related to the angular acceleration, and so torque is decreasing. I is constant, right? And so alpha is decreasing. I can write I as constant. So it's a decreasing there. Okay. F, the mass of the rod is 3 kilograms and the length of the rod is 1 meter. Calculate the linear speed v at point S as the rod swings through the vertical position shown. Okay, so that's not the center of mass. Here's the center of mass, which is 3/4 L. And you can think of its original position as up here. And here's the center of mass at 3/4 L. So we can talk about a conversion from gravitational potential energy into rotational kinetic energy. So I could say, for example, that it's rotating. So then I would say 1/2 I omega squared is equal to mgh. Now, what is h? We want to talk about the difference in the height that we fell, right? So let's say this is h equals 0. So the height, so h here is 3/4 L. And then I can solve for omega I. We already found was 3/5 ml squared. It should have been ml squared, right? 3/5 ml squared. We did that in part A. They gave it to you in part A. 3/5 ml squared omega squared is equal to m times g times 3/4 L. So we can cancel the m's on both sides. We can cancel the 3's on both sides. And then one of these L's will cancel. So I'm left with, so then I want to, let's see, multiply by 10. So I can have omega squared is 10g over 4. And then we want to divide by this L over here, which is 5g over 2L. So omega is equal square root of 5g over 2L. Now, once you have the angular speed, you can definitely find the linear speed at this point, because v is equal to r omega. In this case, r is the entire length of that. That's L times omega. So that's L times the square root of 5g over 2L. So they're saying the L is 1. Square root of 5/2 times 9.8 divided by L, which is 1. I didn't need the mass, right? Yeah, because the omega the mass is canceled, so that was unnecessary information. 5 times 9.8 divided by 2 is I get 4, so I got 4.95 meters per second. Okay, and that was it. All right, well, if I have any mistakes, I'll put the corrections below, as well as the link to the solutions. And yeah.